なんとしい。
Okay. Right.
Are you really ready?
Okay, should we start?
Yes, I'm ready.
Okay. Great. Thank you. Well, thank you for your patience for waiting here. Sorry about the technology. I guess we're a long way apart, and we had trouble yesterday at my university just speaking a few kilometers away. So let me first introduce myself. I'm a professor at Curtin University, where I've been for nearly 40 years now. I started off with the Geological Survey in Western Australia, and I mapped several 1 to 250,000 sheets in the southwest of the state. And I got involved in geochronology in those times, particularly rubidium strontium, and then into samarium neodymium. When I went to Curtin University in the early 80s, we set up a uranium-lead laboratory to run on our mass spectrometer in the physics department. And I guess I became hooked on geochronology, although I still view myself more as a petrologist, a geochemist, and still a field geologist. So if you can have the next slide, please. Right, I want to just give you a little bit of a background, because for this talk, I'm going to use quite a few examples from the Hadean. And as you're probably aware, the Hadean is a sort of time in Earth history when there really actually are no rocks. There's just a set of zircons from around the world, probably now about 17 countries around the world, where we have crystals over 4 billion years. And of course, because of their age, they tend to be very complex crystals. And this is what's sort of bringing up some of the issues in geochronology. So there's quite a bit of debate. So I just thought I'd just set the scene for you before I start the actual talk, to say that I'm going to be talking about, if you can click again, Clementia, you'll highlight Jack Hills, I think. That location there called Jack Hills is one of the best locations in the world, in fact, the best location in the world for collecting Hadean crystals. There's about, I don't know what the current store is at the moment, probably 5,000 Hadean crystals. When you look at the rest of the world, they're in the, well, we can count them mostly on one hand. So if we can have the next slide, please. Yeah, that's the area I'm going to be talking about. That's it. Just a view, so you see a little bit of Australia, probably very different to Colombia. This is considered to be a mountain range almost in Western Australia, very low range of hills. And this is the area which we studied first in 1983. Next slide, please. That's the original outcrop in which we found the world's oldest crystal. That's what it looked like in 1984. It's now almost level with the vegetation at the bottom. Next slide, please. And then this is the belt itself. It's about 90 kilometers long. This is the very first traverse. I took our third-year students to map this, because it hadn't been mapped in detail. We've been back many times over the years, but this was the first time we went up. And again, if you can click Clemencia, I think it'll highlight the W74 site. There it is. That's the site. Oh, yeah, just stay there. Go back. Yeah. That is the location where virtually anyone working on Jack Hills has collected the samples. So that's our W74 site from the original work that I did with my colleague Bob Pidgeon. Those are the traverses the students did. While we have the map, I'll just point out that that W74 site is in a series of sandstones and quartzites. And so we're looking at detrital zircons in there. I do want to point out while we have this slide on, though, because I'm going to come to this at the very end of the talk. Notice around the belt, we have TTG granitoids as old as 3.7 billion years, and we have some young granites as young as, well, young in terms of the Precambrian, 2650 million years, monzogranites. They'll come up in the last bit of the talk. So just bear that in mind, that we have a belt of sedimentary rocks in tectonic contact with these rocks which are older at 3.7, but intruded by the granites at 2.6. Next slide, please. Right, let's get on to the main point of the talk. And because I realize there's a number of students there, I'm also going to go through some very basic things, I guess, for people working in geochronology, as well as some important things at the end. So if I can just go through, why is zircon so important to us? But as you can see from the top, I'll just read through as you look down there. It's present as a primary accessory mineral in intermediate and felsic rocks. It's also present in many mafic rocks, particularly the coarser grained ones, such as gabbro. So it's widely distributed really in igneous rocks around the world. But it also occurs as a detrital mineral in clastic sediments. It can grow in metamorphic rocks if they're at medium to high grade. So it's fairly ubiquitous in many rocks. Yes, we can't find it usually in ultramafics, although there are examples of ultramafic rocks which do have zircon in them. So it can occur in most rocks. Now, what's particularly important about it, it's a strong mineral, that it's stable under most geological environments. It's got a very simple silicate tetragonal structure, ZrSiO2, but it does contain trace amounts of other elements. These can either be substituting for the main minerals there, or particularly zirconium, or they can fit in sites within the lattice. And these trace elements are principally uranium, thorium, hafnium, titanium, the rare earths. But very important, there's no lead. In good zircon crystals, there should be no lead. Lead, of course, the atomic sizes of the atom is too big to fit naturally into the structure. But this is important because uranium and thorium undergo radioactive decay within the zircon crystal. And so we end up producing lead as a daughter product. So if you combine all these factors, it's the mineral of choice really for geochronology. This is nothing to say we don't need argon or even rubidium strontium, but certainly zircon is the one that people would like to find and give a very precise age. Next slide, please. Just again, the very first geology example of zircon, a strong structure, as I mentioned. Essentially, in an igneous rock, it will consist entirely of prisms and pyramids. Next slide, please. Next, yeah, thank you. This is a view of the 100 and 001 structure of zircon. So what you can see is this strong interlocking, but with spaces in which we can, in fact, allow these substitutes of these elements which I've listed below. It's also very resistant to chemical alteration. It'll survive most geological processes. Some people believe it can go down to the mantle transition zone at 450 kilometers and come back up again. And so it's also very important because it's the only known mineral to record Hadean ages. It doesn't mean that there aren't any other minerals which are over 4 billion, but we have no way of dating them. Next slide, please. Right, again, for the people who are not familiar with geochronology, I just wanted to go through the very basic technique of how we get the zircons out of the rock. And this is the basis of really the modern geochronology. And I'm using actually the SIMS, the secondary ion mass spectrometry technique here. But as long as you can get the crystals out, you can analyze them by the methods. So it's very important that your sample is clean. You remove the weathered material and that you wash and crush that rock. You separate the zircon using heavy liquids and magnetic separation, or you can use this electronic disaggregator called the Selfrag. That's made in Switzerland. It's quite a useful machine. It puts about 100,000 volts into the rock underwater, and it breaks along the crystal boundaries. So this is how we get fairly good crystals out of a rock. When you mount those crystals and you've concentrated them, you can either do this randomly if you wanted to take an overview, or you can select the best grains, free of inclusions and alterations. And you would do that if you wanted to find a good igneous age for the rock. You mount the zircons on double-sided adhesive tape, you put them into a resin mold, and then when it's dry, you can polish the zircons in half, because you want to look at the internal structure of the crystals. Firstly, we normally photograph them in transmitted and reflected light. Sometimes we mix the two together because we're looking for inclusions and things we don't want to hit when we analyze them. You coat the sample with gold, and you obtain cathodoluminescence using an SEM with a CL detector. You can use that, you can just use a carbon coating, first if you want to, but then you've got to remove it because we need a gold coat if we want to put it into the SIMS. We analyze it then by mass spectrometry. Okay, next slide, please. Here's an example of a zircon. This is one of the standard zircons. This is Richard Stern's OG1. This is a very good standard because it's Archean in age. If you look at the top one, you can see the crystals. Some of them are nice tabular with pyramids on the top. Some of them are more stubby and rounded, but they all give a very consistent age. In the lower part of that image B there, you can see what the CL pattern is. So these regular bands going across the crystal, they show variations in the gray shade from white to perhaps even black in some cases. This variation is due to the trace elements. It hasn't been defined that well at the moment. We have an atom probe at Curtin, and we're starting to look at what actually makes up, or what the elements are within those particular bands. Next slide, please. Let's just look at the zircon morphology first of all. This is a typical igneous zircon. It shows what we call oscillatory zoning. That zoning is very like the zoning in plagioclase. It's interpreted as a growth zoning. And here is this variation in color, which is reflecting variations in uranium and other trace elements. Next slide, please. Here is an example from Fernando Corfu, and I've highlighted the bottom one, which to show you what metamorphic zircon looks like. So you can see on the right-hand side there, it often is if it's a detrital zircon, it often has a pitted surface. But if it's a metamorphic zircon, it has these high angle faces. In other words, those crystallographic faces you can see, they're not the prisms and the pyramids. They're completely new faces, high order crystallography. Next slide, please. And here's an example then. There's two things that you find with metamorphism. You can either grow new zircon or you can recrystallize existing zircon. So here's an example of recrystallization of an igneous zircon. The one on the left from Schalltiger, if you can see it there, there's actually oscillatory zoning in the middle of that crystal, in the core, and that has the oldest age. Then there's a band you can see cross-cutting there on the left-hand side of the crystal. In other words, it's undergone some later event, probably metamorphism, maybe igneous even in this case. And that is slightly younger when it was dated. And then there's a very tip on the very bottom there, which is dark, and that is 100 million years younger. So that's a metamorphic feature. The one on the right is a set of images from the study I was involved with in Derbyshire, which is the ultra-high pressure zone between the North and South China cratons, very famous zone for UHP metamorphism. In the center, we have oscillatory zoned igneous cores, and around it, we can see metamorphic zircon. Now, much of that metamorphic is not new growth, but it's recrystallization of the original igneous grains. Next slide, please. And here again, people often talk in geochronology about core rim structures. So I thought I'd just better mention this. On the left is an oscillatory zone magmatic zircon. As we move across to the right, we have what is known as a metamict core. Metamict simply means it's altered, and it's usually the result of radiation damage. So there's a messed around core, and then it's got igneous zircon around it. So that's an inherited zircon. It's got an older portion in the middle, the core, and a rim. And as we move to the right, the next one has a magmatic core, which has got oscillatory zoning, and it's got a metamorphic rim, probably just recrystallized. And then the second from the end has a metamorphic core and a magmatic rim. That's not very common. And I leave the interpretation of the one on the right to anybody because it's not very clear from what we can see. Next one, please. This is the best example. This is from Gerhard Wawra, the guy who really characterized metamorphic zircons. These are the soccer ball shaped zircons with these high angle faces, and that is new metamorphic growth. So these are new crystals. They're not recrystallization of pre-existing ones in the rock. These are new zircon growth. Next slide, please. I just thought I'd give you an example of anatectic granite and anatectic zircon, sorry. This is a study I was involved with in North China many years ago. And what we have at the top is the geochronology for a garnet granulite. That granulite underwent melting and produced a garnet-bearing granitoid, which is the one on the bottom there, the diagram. Identical in age, but when you look at the two diagrams on the right, what you can see is some rounded zircons, and also, if you look carefully, the elongated one has a recrystallized rim. But when you go to the bottom diagram there, on the far bottom right, you can see water-clear crystals of new zircon growing. They're not very well developed, they're incipient growing, but those are igneous zircons growing in the granite due to anatexis. Next slide, please. Just to show you detrital zircons, I mentioned we're going to show Jack Hills quite often. This is from Aaron Kavos's PhD. These are the Jack Hills zircons put onto double-sided tape. You can see that most of those meet the bill for igneous zircon. They have the prisms and they have the pyramids. Some of the pyramids are a bit rounded. It is a detrital suite, so it's probably been eroded to some degree. There's no evidence at Jack Hills of metamorphism. We haven't been able to establish that. Okay, next slide, please. But some of the Jack Hills crystals are less well formed, and here's a whole suite of them. This is where we have a problem. Often with zircons, we can look at them and say, oh, this looks as though it's older, this looks as though it could be younger. Jack Hills zircons look all the same. So we don't know whether, if we picked one of those crystals, whether it would be 3 billion years in age or 4.4. We just can't tell the difference. They're the same color, and they give differences in age. Next slide, please. Okay, let's go through the geochemistry, geochronology of zircon and build up the story here. What trace elements are useful in geoscience? Well, we have the rare earth elements, for instance. Now, they could help us with characterizing the source, and I'll show you an example in a moment. We can also analyze titanium, and with titanium, we can do titanium in zircon thermometry. And that allows us to calculate the temperature at which that portion of the crystal you analyze crystallized. Okay, now we have the isotopes. We can analyze lithium 6 and 7 in particular. That also helps with the source characterization. We can use the 3 isotopes from a melt that came from the mantle, or was it a crustal melt? We can also look at lutetium hafnium for source characterization, particularly when it goes back to the mantle. But in particular, we want to use uranium, lead, and thorium for the age determination, which we'll look at first. Next slide, please. Next slide, please. Right, very simple, radioactive decay. We got an atom. It can give off rays, such as gamma rays. It can give off particles, alpha and beta particles. Next, please. But this is the more realistic chain. Here's uranium-238, which is one of the principal elements or isotopes that we look at. If you go to the far right at the top, you've got uranium-238. It then goes through a whole series of alpha and beta stages, producing a whole range of minerals elements along the way. It ends up at the bottom left there with a stable isotope, which is lead-206. So these are the two things that we'll be looking at. So the thing is really complicated. We tended to treat it fairly simply. Next question, the next slide, please. Here are the 3 isotopes that we normally analyze in geochronology. So we've got thorium-232 at the top there, uranium-235, uranium-238. The daughter isotopes, respectively, are lead-208, 207, and 206. The half-life, very high for thorium, 14 billion years. Intermediate for uranium-235 at 0.7 billion years, and uranium-238 is 4.47. We have a decay constant geological. Normally use the thorium because the thorium tends to be more mobile in zircon, but it's a useful thing to measure in any case, particularly when we're looking for concordance. We use the 2 lower ones. We use uranium-235 and uranium-238. And the advantage of that is one is a long-lived scheme, one is a fairly short-lived scheme. And if we have those two, then what we can do is we have 2 different methods of determining the age from the same crystal. I just put at the bottom there that the standard to use these things is when do you use a particular age? We use lead-206 against uranium-238 if the age is less than about 1.2 billion years, but we use the two lead isotopes, 207 and 206, if it's an older crystal. Some people use 1 billion years, but we tend to use a slightly higher age there because the reason you swap over is because of the error in the data that you collect. Next slide, please. Now then, it's very important. You've got your data. How do you plot your data? There's two sets of diagrams you can use. They're called Concordia plots. The one on the left is the Terra-Wasserberg plot. One on the right is the Weatherall plot, named after the guys who first used it. What we want is, if you can see the curve on there, it's actually shown on the right-hand diagram as Concordia. If your zircon plots on that line, then you're happy that it's a pristine zircon, that it's giving you a reliable age. However, if it isn't on that line, and it falls on a line either above or below that, we call that a discordia line. And as you can see in the diagram on the line on the right, if you look at T0, that's the age at which the crystal formed. It underwent an event at T1, and the zircon, any zircon formed at the first event, lost lead along that discordia line. It could also gain lead if it plots above the line. People used to think that was uranium loss, but in fact, we now think that's more likely to be lead gain. So we can use either of those diagrams to plot our data. Right, next slide, please. And here's a real-time or real-life example of both those plots, the Terra-Wasserberg on the left, the Weatherall on the right, showing data from ancient zircons. The one on the left is Antarctic zircons from the Napier complex. The age of the rock is around about 3.8 billion years, but it underwent an event around about 2.5. So you spread all your data along both along Concordia and along the Discordia, but you also get what we call reverse discordance. The Jack Hills one on the right shows a different set of scenarios, because what you can see is they all seem to plot downwards. In other words, it's a lead loss trend, and they plot close to zero. Now, the one on the left, the Antarctic one, we believe that the disturbance of the igneous crystals was due to very high temperature metamorphism at 2.5 billion years ago. With the Jack Hills one on the right, we think that the disturbance is very young. It goes almost to 0 million years in the bottom left corner there of that diagram. So we believe that is due to extensive weathering in the Cenozoic, 30 million years of laterite formation on these rocks. So we've got the two things there: reverse discordance when it goes above the line, and normal discordance when it goes plotting below the Concordia curve. Next slide. What we have here then is an example of the analytical techniques we can use. I've shown you the CL4. The top is a line of CL. The bottom line there is a line of backscattered electron images, all taken with an SEM. Now, this is an important point that not everyone appreciates, but there is a difference in the pattern in CL than there is from backscattered electron. Let's take that fat grain more or less in the middle there. If you look at that big grain second from the right, you can see it's got a dark core. But you can see when you do it in backscattered, it's got a light core. And what's the reason for this? Well, in CL, light patterns generally indicate that it's low in uranium. So dark pattern at the top there, low uranium. Light patterns indicate it's low uranium. Dark patterns indicate it's high uranium. I apologize there, I made an error. In CL, light patterns indicate low uranium, dark patterns high. So it's a uranium-rich core in the CL. However, it's light in the other one because the backscattered electron images are the reverse. So when you look at these things in published paper, make sure you can see whether they're using backscattered electron or whether they're using cathodoluminescence. Next slide, please. The other important thing is you need to take very good quality CL images to see the intricacies inside the crystal. This was a student of mine, Matthew Grant, a few years ago, who took a long time to obtain his images, but he got very high quality images. If you look at image F there, for instance, you can see the numbers at the top left. Image F, what you can see in the middle is oscillatory zoning, but then you see this very light band going through there, which is cutting across that. This was quite important because you could actually put an analytical spot in the center there, and then you could put it on that band, and hopefully you could work out the time in which that crystal underwent some sort of alteration. Next slide, please. Right. Having got your analysis, and I'll go through that in a moment, it's very important also, particularly after SIMS analyses, to re-image the grains. This time we do it by backscattered electron. Why? Well, we want to look if there's any imperfections in the pit, which is less after the analysis. Because if we've hit an inclusion, we'll have bad data. If we got a crack in the crystal, we'll have bad data. So we want to make sure our data is good. And if there's any indication of lead mobility in our data, then we need to do another technique which is called ion imaging, and I'll mention that a bit later. Okay, next slide, please. Right, analytical protocol and techniques. What are the instruments that we can use to get good zircon data? There's three techniques widely used today. The first one I put is secondary ionization mass spectrometry. That's SIMS. It's excellent for complex zircons. It's the only way to look at complex zircons because you can put multiple analyses within a single crystal. TIMS, thermal ionization mass spectrometry, is seen as the gold standard, but it only works if you've got a simple igneous system. In other words, the crystals are all the same age. Once you start to add difference in ages, then you'll mix them together because generally you're analyzing a larger proportion of the crystal. Originally, we used to analyze multiple crystals, which was fraught with disaster. So there's a lot of very strange ages in the old geological literature. It works very well. People are now getting smaller and smaller volumes that they can analyze, but it still has some constraints. And it's, of course, totally destructive. The other way, of course, is ICP-MS, inductively coupled plasma mass spectrometry. That gives you a very rapid analysis. It's useful in some ways, but it has some deficiencies as well. The other thing you want to do, additional analyses that you can undertake to get make sure you've got really good data, is to use the SEM for imaging. You've got the CL and the backscatter, as I mentioned. You can use TEM, transmission electron microscopy, very good for crystallographic details. You can use the electron probe, get a complete mineral analysis. You can also use an atom probe. This gives you the nanoscale. You can actually see individual atoms using an atom probe, and I'll show you an example of that right at the very end. And you can use your Raman spectroscopy, which will give you the chemical structure. And people are trying to use synchrotron, but at the moment, it's not very widely used because it's not giving information that can be interpreted very easily. Next slide, please. Okay. So what can we analyze in zircon using SIMS? And I call this the zircon alphabet. Next slide, please. These are the elements that can be almost readily used, not by every laboratory around the world, but there's quite a big range of elements that you can actually determine from a zircon. Some are more important than others, and some are only just being developed. In terms of like silicon isotopes, which people are trying to do. In fact, zirconium isotopes can also be done at the present time on certain machines. But it'll fill in over the years as the instrumentation improves. Next slide, please. Let's look at uranium, thorium, lead system. Yep, let's go to the next one. Next slide. These are the two main instruments that are used today, or the two main manufacturers at least. On the left, we have the shrimp, which was originally built in Australia. It'll be built in China from this year. And this allows us to do uranium lead. This is the original instrument that is 25 years old now in Australia, in Perth. On the right, we have the Kamika. This is the IMS 1270 in Edinburgh. Now, this can also be used for oxygen as well as uranium lead. These instruments are expensive. They cost about $4 to $6 million each. And in fact, if you want the latest Kamika, which is the Kamika IMS 1300, it's going to cost you about, I think it's 10 million euros or something like that. It's not cheap. Next slide, please. Okay, we need an analytical protocol. If let's say we want to do multiple analyses of isotopes on our zircon. What order should we undertake the analyses? Well, I've listed the order there, 1, 2, and 3. If you want to do the analyses, you should first use SIMS because you have a smaller pit size. In other words, you remove less of your crystal. You've got more to work with in future. So you can do first the uranium lead. Then you can do the oxygen. And only after that should you use ICP-MS because it makes a much bigger pit. You lose a lot of material with this. But it's the best way, of course, for doing rare earths, although you can do rare earths by SIMS as well. It's a little bit more time consuming. But ICP-MS is best used for the lutetium hafnium. If you look at that diagram, which comes from Aaron Kavosi, you can see there's 2 analyses which we wouldn't recommend. And they're the ones on the right, top right and top left, because they intersect a black band as well as going on another portion of crystal. So that would show you these are not the places to put your crystal because you're going to get a mixed age potentially. We want the 2 lower ones. If you look at the little diagram at the bottom, you can see that the pit for uranium lead analyses, it's about 20 microns across, 25 microns possibly, but only 2 microns deep. Okay, so we have those data. We now later on want to analyze oxygen. We can either put it directly into that bottom of the pit, because we found, even though we use an oxygen beam to get the uranium lead data, it doesn't impact and implant oxygen into the zircon itself. But some people would like to remove about 5 microns and put a new pit in there. That's fine, as long as you've got the imaging to show you are in exactly the same spot. Okay, you've now got your oxygen data. You want to do rare earths or lutetium hafnium, so you use the ICP-MS, and this creates a bigger pit. You're lucky if you can get a 6 to 8 micron pit, by the way. Usually the pits are much deeper than that, and they're also, as you can see, the diameter is also a lot bigger. But if you don't use that order, if you do number 3 before number 1, there's not much of your crystal left to do the uranium lead analysis. So it's very important to follow the correct protocol there. Next slide, please. Righto, how many analyses would you require? If it's a simple magmatic rock, you can certainly get away with 10. In other words, when you look at your machine as it's collecting the data, if you can see that every age is the same, well, why keep going? You can only do about 30 in a 24-hour session. So let's cut the losses, if you like. We have enough data if you've got 10. If the magmatic rock, however, has inherited zircon, or there's complications to the zircon ages, you're seeing the variation, then you have to do at least 20 or 25, maybe even more. For detrital studies, you need at least over 100. I think the theoretical one is more like 120 analyses. That's to make sure you get 1% of the population, potential population in that particular sediment. As you can see, if you can only do something like 30 SIMS analyses together with your standards in a day, it's not the best way to do provenance studies. So you need an alternative technique, and most people then would use ICP-MS. Next slide, please. This is an example from our famous old crystal. The bottom right there, the 4404 plus or minus 4 million years. It's the oldest age recorded from a terrestrial zircon. There's older ones from the moon and Mars, Martian meteorites now. This also shows you the analytical pits put into the crystal. It shows you that the crystal is cracked. And when you look at the cracks, the zircon ages are younger. So we have a range of ages from 4.2 to 4.4. So this is the problem with old crystals. They get very complicated. Next slide, please. Here's a Concordia diagram, a Weatherall diagram, and the one on the right, close to 4.4, is that site I showed you. It's a concordant grain, or concordant site, I should say, because it intersects Concordia. The other zircons in there, or the ages, are younger. So the initial age is a concordant one, and then it spreads down with that a normal discordance. Next slide, please. Let's look at oxygen. Next slide, please. Again, this is the Kamika 1270 in Edinburgh, where we obtained the first oxygen data on those old crystals from Jack Hills. Next slide, please. Here's an example of Hadean crystals from Aaron Kavosi, his PhD with myself and John Valley. What you can see at the bottom there, or at the bottom of each diagram, or each zircon, is that every one of those crystals is over 4 billion years old. Some of them are 4.3, some of them are 4.1, blah, blah, blah. You can see that the texture in there, or the structure, I should say, internally in the crystals, some of them are nice oscillatory zone, some of them are very patchy. The other values that are shown on there with the small spots are in fact the oxygen sites. Now these vary as well. If you take the bottom right crystal, you can see that there's some values of 5.6. When you look at other crystals, you can see that they get up to 7.2. I'll point out what that means in a minute, but what you can see is you can analyze multiple sites, both for age and for oxygen, on a single crystal. Next slide, please. And here is very early data that we collected in the 80s from these Jack Hill zircons, which illustrates an important point. What we have here is the way we present the oxygen data. These are delta O18 in the zircon per mil. In other words, parts per thousand, not percent. And it's relative to Vienna's water. I don't have time to explain this. If you want to go into it, it's easily to find on the internet. But what I want to show you is that the data that we collected in our first study is the one at the top right of that diagram, where you've got a series of analyses of oxygen from the 4.4 billion year old site way back down to about 3.2, 3.0 site, and they show a spread. They show a spread from the mantle value, which is 5.3 plus or minus 0.3 per mil. So if your rock had a parent which came from a mantle, a magma that came from the mantle, it should have zircons which had that value. You can see they're elevated above that. They go to about 7.5 per mil. How can you elevate the oxygen? Well, it tells you that it didn't come directly from the mantle, that it came from a rock. Yes, originally it did come from the mantle, but it had been weathered, it had been turned into probably a sediment, and it had been melted later on and produced a new rock. It had interacted with the atmosphere at the surface of the Earth. Why is that important? Well, what it shows you is way back at 4.4 billion years, the pattern, even though it's more diffuse and spread in that set of data, is identical to what you can see on the left for the Superior province in North America, which ranges from just under 5 per mil to 5 mil, and then goes up also to 7.5. So this led us to the hypothesis of a cool early Earth, which we published way back in 2002. In other words, way back in the Hadean, there was no difference in the oxygen signature of the zircons than there was at the end of the Archean at 2.6. That's an important point. Next slide, please. However, when you plot the data through time, it looks a bit washy to me, but I hope you can see that diagram. This is the result of data now which goes up to the present day. And so if you can pick out the mantle line there, you can pick out, there's a range where we don't get above 7.5 per mil until the end of the Archean. And then we gradually move up towards the top left of that diagram. And in other words, with time, many rocks contain zircons which have elevated oxygen, up to 11 per mil. And that is really a result of massive crustal recycling, usually during a supercontinental cycle when we're actually disrupting and producing new continental crust. Next slide, please. Let's look at lithium. Next slide. This was done for the first time on zircon in this laboratory. This is the Kamika 1280 at the University of Wisconsin in Madison, with John Valley at the back there hiding behind the instrument. Next slide, please. Here are two Hadean crystals, 4066, 4229. And what we're showing at the top is the gray image is the CL of those two zircons in a small area. On the right, those two blue ones, they're electron probe data. So the probe data is showing the lighter the color, the more lithium. And so what you can see is broadly the lithium seems to follow the CL pattern. So we argued that the lithium was a primary feature in that zircon crystal. That is debatable because lithium is a very mobile element. And in fact, it's shown to be very amenable to moving in zircon. Next slide, please. what did that data mean? Well, as this was the first study of zircon, we had nothing to compare it with. So all we could do was to compare it with lithium values for rocks at that time. Now, these data are plotted as delta 7 lithium in per mil. Again, let me have a look at the two bottom images there. If you got a meteorite or a rock from the moon, you'd see there's a very narrow range of lithium. So the bottom diagram, narrow range. If you've got a fresh mid-ocean ridge basalt or an ocean island basalt, a very narrow range. But when you start to alter them, the more, etc., you start to spread out and get a range of values. Next slide, please. And if you look at the bottom two diagrams, you can see when you look at the continental crust and you look at high-level granites, pegmatites, and you look at the middle diagram, which is continental weathering, laterites, saprolites, shales, etc., you can see a spread. At the top diagram, you can see the spread we got from the Jack Hill zircons. So we argued from this that by using delta lithium, we could substantiate the story with oxygen. In other words, we can say that the rocks were formed from pre-existing material that had been at the Earth's surface and had undergone weathering. Next slide, please. Okay, what can we analyze in zircon using SIMS and or ICP-MS? Let's have a look at the next slide, please. We can look at the rare earths. So we've got lanthanum together with the rest of the rare earths. Next slide, please. And here are more zircons from Jack Hills. There's a bit more of a range. A couple of those are, well, one of those is in fact not Hadean, but that doesn't matter. What is shown here is the oxygen data now together with the numbered spots. So you can see 1, 2, 3, 4, 5, etc. Those are the sites which we analyzed using a Kamika IMS-4, and that actually allowed us to collect the rare earth data. If that had been ICP-MS, those spots would be bigger. Next slide, please. Okay, this is what we got. These, in fact, are some of the oldest zircons from Jack Hills. But very importantly, that pattern is identical to the pattern you would get if you analyzed a Cenozoic igneous rock. In other words, that is the pattern of igneous zircon, and it hasn't changed over geological time of 4 billion years. What are the key features of that diagram? Let's go from the left to the right. You can see there's a positive anomaly in cerium. That's because there's always been oxygen. If you look at lunar zircons, there is no positive cerium anomaly. So that's characteristic of all Earth zircon. And we also look for europium. Europium is famous, you know, for its anomalies, and we have the negative europium anomaly. But then we have this increase from the middle rare earths to the heavy rare earths. As we go from left to right, from the middle of the diagram to the top right, you can see that they're slowly increasing in number relative to the, this is ratioed sample to chondritic meteorites. In other words, primordial material that made up the Earth. Next slide, please. Here's a simple diagram from Urs Schaltagger showing magmatic zircon at the top. He's shown perhaps less of a cerium anomaly and a bigger europium anomaly. That doesn't matter. But the important one is the second part of this diagram, which shows metamorphic zircon. Notice the difference in metamorphic zircon. Instead of showing this progressive increase from the middle to the heavy rare earths, it shows an increase in the middle and then it tailors off. It becomes less heavy rare earths. Why is that the case? Because garnet is crystallizing at the same time, and garnet likes heavy rare earths, and in fact it beats zircon in absorbing those heavy rare earths. So if you've got garnet crystallizing, you bring down this tail. So it's a good indicator then for metamorphic zircon, particularly high-grade metamorphism. Next slide, please. Just to emphasize the point, here's a real-life example, again from the Derby Sulu ultra-high pressure belt in China. Two diagrams on the right, one just shows the igneous data, the one on the bottom shows a gray field, which is the igneous data, and it shows the metamorphic data. It wasn't disappearing entirely, but you can see a flattening of the curve. And so, again, it shows that this thing really works. These are eclogites from the Derby Sulu belt. There are also other variations in the other two diagrams, which I won't go into, which show that if you use the trace elements in the zircon, you can still discriminate between a metamorphic and an igneous zircon. And we're going to use that in the next slide. Next slide, please. These are the rare earth data. This was a study undertaken by Grimes a few years ago, 2007, as you could see. One of the criticisms we had when we first described the Jack Hill zircons was we said they came from continental crust. And several workers said, no, we believe they came from Ocean Island and they were therefore oceanic crust. I think we never accepted that argument, but Grimes' data are really good because what you can see, let's just use the two on the right, you can see there's a continental zircon field and an oceanic zircon field. What we have plotted in there are the Narrier terrain, which is where Jack Hills resides, and the other one is Acastonisis. These are the oldest rocks in the world from northwest Canada, and they all plot within the continental field. And notice what he's using: uranium, ytterbium, and plotting that against it. Is that yttrium? It's certainly the right one is yttrium. I can't read the other one on my screen at the moment. But by using these trace elements data that we've collected, the rare earth data, we can actually work out, and this is particularly important for detrital zircons because we don't have a parent rock. Next slide, please. Let's look at titanium. Next slide. Here is titanium in zircon thermometry, a study we did with John Valley and Bin Fu. And what we see when we collect the titanium thermometry data is that we get a big spread of ages. We don't just get a very nice peak of ages. The top diagram is the Sierra Nevada batholith, granites, tonalites, etc. from the United States. 674 degrees plus or minus 64, big error. The next one down looks at leuconorites and anorthosites. They tend to be a bit further to the right. In other words, they're higher temperature. That's what you'd expect. They're related to mafic rocks. The one below is a mixture of gabbros, also fairly high temperature. The bottom are the Jack Hills zircons. You can see there's a spread, and we get an average temperature of 717 degrees plus or minus 54. You can see from that diagram they overlap. Go to the next diagram, please. Next slide. And here we have the whole set of data from Bin Fu's experiments. And I don't want to read them all, but they're kimberlites, they're granites, they're gabbros, they're anorthosites. The red line is a line which you could put basically through all your data. The only ones that miss out are the Kimberley diamonds at the very, very bottom there. So in other words, you cannot use the temperature to tell what the zircon crystallized in. Again, if you've got a detrital zircon and you're trying to use this to work out what the parent rock was, you can't do it because there's almost a complete overlap. So yes, titanium in zircon thermometry may have its place, but be careful how you use it. Next slide, please. Okay, what can we analyze in zircon using ICP-MS? Next slide. It's lutetium and hafnium. Next slide, please. Right, this is one of the latest machines. This is a laser ablation split stream at the Swedish Natural History Museum. This setup is called LASS. It's the sort of state of the art at the moment because on the left, you can see advantages. Unlike the standard ICP-MS, you can run uranium lead together with, at the same time, lutetium, hafnium, and all rare earths. So you're collecting simultaneous data, which means that you can relate your age directly to the data you get for lutetium, hafnium. The disadvantage, it's still fairly large pit, it's quite destructive. But how do you do that? Well, if you look at the little diagram at the bottom, I won't go through the whole details, but let's start with laser. You hit the sample with a laser, you take the sample material out, and it's put into two mass spectrometers. So you can collect the uranium lead at the same time as you can collect either lutetium, hafnium, or rhenium, osmium. It's quick as well. You can run 500 analyses a day using any ICP-MS setup, actually. It's very easy. It takes longer to put in the points than it does for you to sit around and look at the data. Next slide, please. Okay, let's have a look again. We'll use the Jack Hills example, a former PhD student of mine, Qian Wang, who's now working in China. And these are her data from Jack Hills. She's got 1,093 data, all of which had zircon discordance less than 10%. So we consider these to be good data. So we have this diagram now, which is one you'll see used a lot for lutetium hafnium data. It's got on the left-hand side epsilon hafnium at the time of the crystallization, and at the bottom, it's got the lead 76H. What you can see is there's quite a spread of data in there, but let me just point out, you can see mafic crust in there. UCC is upper continental crust. What people try to do with these type of diagrams is to work out the environment, if you like, where the zircon may have crystallized, and also when it crystallized. You can see there's at the top two versions of depleted mantle. One is the arc mantle, one is the depleted mantle, and we've got a line there at 0 called Chur. That's the chondritic bulk earth value, which we also use in neodymium work. That is the starting point, if you like, for the earth, and you get variations for that as the earth evolves. So as the mantle gives rise to more and more rocks, it melts, it follows this depleted mantle line. There's some controversy when that starts, but I won't go into that. The other point is that as you start to form rocks, you start to rework them, you remelt them. And then what's the key point of that diagram? Well, if you go from Chur positive up to 5 and 10, it indicates you've got new material coming in from the Earth's mantle. But if you go the other way, negative values in epsilon hafnium, it means you're reworking the crust. And what you can see is -5. And in fact, in these Jack Hill zircons, some of them go back to -20. Right, so the other thing that people do on these then, if you've got an igneous rock, you can be more precise and say, oh, I know it was in mafic crust, so I follow the mafic line. But if you've got detrital zircons like these, you've got to see how they fit with the model. So if you follow the mafic crust back, you can see that some of the zircons would be along that line. But we also find that the upper continental crust is also where some of the data plot. So it suggests then that these detrital zircons have a range of different parents from mafic to felsic. But remember, when you plot this thing back, you want it to either intersect the Chur line or the depleted mantle line. And there is a problem, because this is only a model age. Some people use this as though it's a real age. It's only a model because, particularly with detrital zircons, you don't know what the parent is. Okay, next slide, please. Okay, now I want to get on to the final part of the talk, which is what are some of the problems we have with zircon analyses and how can we resolve them? Next slide, please. I'm just going to focus on 2 of them. I'm going to give you several examples of lead mobility, and I'm also going to come back to this issue about the hafnium data. Next slide, please. Let's take as a case study 1, lead mobility in the Napier complex in Antarctica. You can see a little diagram there which shows Antarctica, a lot of ice and snow, and what they call nunataks, which are the mountains or the rocks that stand up above the ice sheet. I've indicated 3 sites there which have been worked on for the last 30 years, which is Gage Ridge, Dalwitz Nunatak, and Mount Soames. Now then, we know that parts of the Napier complex are older than 3.8 billion years, but we've never proven that they're Hadean, although we have although we have Hadean ages from some of the zircons. We know it was metamorphosed twice, firstly at high grade at 2.8, and then at ultra high temperature, 2.5. These are some of the hottest rocks on Earth. The temperatures are well over 1,000 degrees Celsius in that late event. We know that the zircons are complex. The very first SIM studies using the shrimp in Canberra in Australia indicated something was going funny with the crystals. And Ian Williams and Lance Black, papers in 1984, 1986, identified this for the first time. Next slide, please. Here are some of the data, Williams on the left, and a later version from Kelly and Simon Harley on the right. You can see there from the location we're talking about, Gage Ridge. So what we have here, if you look at the top left diagram, you can see all those data which plot above the Concordia curve. Can you click the button again, please? Next click. No. Yeah, that's it. That's what I want to emphasize. The massive data which you get, which is reversely discordant. In other words, it's lead gain. How do you explain that? And you can see from the bottom diagram of Kelly and Harley, yes, they're reversely discordant, not to the same extent. Next click, please. Next slide, or next click. There it is. So they go just above it's not as advanced as in the previous one, but it's there in any case. Next slide, please. So here we wanted to reinvestigate this together with the Marie Curie Fellowship to myself and Martin Whitehouse, which is Monika Kusiak from Poland. So these are published with Monika as the first author. So what we have here is Dalwitz Nunatak on the left, Gage Ridge on the right. And what you can see here is this smearing of the age data along the Concordia curve, mainly clicking down to around about 2.5 billion years. So it looks as though, again, this is this effect of ultra-high temperature metamorphism. But importantly, we've got these reversely discordant crystals at the top. When you look at the diagram from Gage Ridge on your right, you can see there's only a few points which are reversely discordant, but there's a nice discordia line down to 2.5. Now, the important point why these are color-coded is it shows you that most of these crystals, or most of these analytical sites, are low uranium. And so if you have low uranium, you think you wouldn't have much disturbance of the crystal because it shouldn't have undergone the spontaneous breakdown to the daughter products. You expect this to be the high uranium grains. It's important that they're not. Next slide, please. And again, okay, and the next slide. Right. This is a plot of a SIMS analysis. And this is what we would get data off the machine. So we would analyze usually 1, 2, 3, 4, 5, 6, 7, 8, perhaps up to 10 analyses on exactly the same site. So we would collect the whole set of data. If you look at the top one there, the lead 206, look how spiky it is. People call this lumpy lead. It's usually 206. It happens once in 207, but 207 is flatter, and uranium 238 there is flat. And the other ones I haven't labeled. If they're flat, it tells you you're going through a uniform crystal. But hey, when you look at the lead there, there's something funny going on. It's spiky. So this suggests that the lead is decoupled from the parent uranium, because uranium isn't showing any spikiness. So this suggests we have the lead moving within the crystal. We can pick this up in multi-collector mode. We can pick it up in monocollection as well. Next slide, please. So how do we address this problem? We now go to Stockholm. This is Martin Whitehouse's equipment. It's also a Kamika IMS 1280. And next slide, please. This is our strategy. And we've applied this now to looking at these very old crystals. There is a software program called WinImage for the Kamika. So we are able to image a 70 by 70 micron square using this machine. Unfortunately, we can't adjust that. It's fixed. That's how the machine is. We've used a primary beam of 2 micron size. We flood the chamber where the sample is with oxygen to enhance the lead yield. And then we acquire data between 50 and 100 cycles. In other words, we analyze for up to 40 minutes. Now, we can do this in monocollection mode, and we can get yttrium, we can get hafnium oxide, lead, titanium, thorium, and uranium oxide. However, importantly, in the multi-collector mode, we can look at the isotopes. So we can have lead 204, which is the non-radiogenic isotope that we always model to. We can look at lead 206, lead 207. We could do 208, but we haven't done that because we probably need to know the thorium a bit better. We can modify the detector. We can use hafnium oxide as to see the machines running well, and then we can image process on what is known as the WinImaging tool. Now, this has a very big advantage because you don't have to do it while the instrument's running. You can collect images, and I'll show you in a moment how this is done. Next slide, please. Here's an example of the monocollection mode of a zircon. We've never published these data yet, but this shows essentially major elements within a zircon from Antarctica. This is one of our Gage Ridge samples. If you look at that far left diagram, it's aluminium. And you can see this thing that looks like a tree. What these are cracks going through the zircon. If you look across, you'll see that lead shows exactly the same pattern. Identified. So lead and aluminium are coming in later along cracks in the zircon. Calcium shows that to some extent, but not as strongly. We look at phosphorus, it doesn't seem to be affected by these cracks, neither does titanium, although it looks variable. And then yttrium looks very strange because it's showing a very strange pattern, which you can actually see in the lead as well, where there's a sort of some sort of structure in that crystal. Okay, so it's all very interesting, but that's showing us a later phenomenon. Next slide, please. Here we have Mount Soanes, Dalwitz Nunatak, Gage Ridge, zircon, 2 zircons from each, and we can show the patterns. This is the iron imaging you get. So you can look in the bottom left corner of each of those colored images, you can see what, across the top, we've got lead. You can see how lead varies in the crystals. And along the middle line, we've got hafnium, and along the bottom line, we've got yttrium. I'll point out that 3 along, you can see A in the under Dalwitz Nunatak, you can see that the yttrium is following the oscillatory zoning in that crystal. Next slide, please. There, I've changed them. We kept lead at the top. Now we have uranium, and at the bottom, we have titanium. Interestingly, now on the bottom left, we can see variation in the color for titanium. The lighter the color, the more titanium in that site. And so what we're seeing is titanium is mobile. Remember, we want to use titanium to work out the temperature. If titanium is mobile, it's not going to give us the right answer. It's going to show that it might give a temperature too high or too low. Okay, but we can see there's some variation in those elements. Next slide, please. Right, now we can be very clever with this software imaging because we've collected the data separately for lead-207. We've collected it for lead-206. Now we can combine the two, and we can get a 7:6 ratio. And this enables us to calculate the age of this image. It isn't done on the machine, as I mentioned. It can actually be done in your home office if you want to. Next slide, please. Here we show an example of what you can do. You can measure any shape you want to with this imaging tool. You can see on the left-hand diagram, we can look at the general variation between those 2 zones within the crystal. We can put theoretical SIM spots, 20 micron spots, across the crystal and work out the age of that. And then on the right-hand diagram, you can see you can focus in on the very small sites which are the richest, which have the highest 7:6 ratio in this case. Next slide, please. And there we can see the ages. On the left, we can see that that part of the crystal is 3377 average age. The part on the right of the left-hand crystal, 3538. When we look at the SIM spots, we get quite a range of values. The lowest value there, I think, looks to be around about 3320 at the top, but we can also go up to 3774. When we look at the image on the right, though, have a look at the 2 on the left. We get 4198, 4129. In other words, we've produced a Hadean age in a crystal which is not Hadean, because we've got a very small spot size, and we're now looking very focused on those little areas there. Next slide, please. Okay, so what are these lead concentrations? When we looked at them, we were not sure what they were. We had the TEM image, you can see. We have like a white spot, and we have a fuzzy zone, and then we have a black zone around them. And they're circular. When you look at the bottom line, you can use the EDEX spectra, and you can, if we work along there, you can see lead. It's very light. The light spots are showing up, so we've got a concentration of lead. When we move to the next diagram, titanium is also concentrated. When we move to the other diagram, aluminium is too. But when we look at the bottom right, you can see it's black for zirconium in those sites. In other words, there's no zirconium there at all. But there is an increase in lead, titanium, and aluminium. Next slide, please. Right, now we took it a stage further, and we look at the high angle annular dark field. This was done with Richard Wirth in Potsdam in Germany, and you can start to work out what the material is. And what we found was that the lead is present as metallic lead. It's not lead oxide, it's not lead sulfide, but it's metallic lead. We found that we had an aluminium titanium rich phase, and we found that the dark one on that little diagram is mainly a silica rich phase. So this was something that no one had found before. Next slide, please. Not only that, but using the HADF, we can also work out the crystallography of the thing, and it's cubic. So it's cubic lead, and that's how we know that it must be metallic lead. We've also done this more recently on a paper where we've looked at it using the nanosims, and we've come up with exactly the same conclusions. These are lead nanospheres in zircon, and they're associated with, in a spherical setting, with silica and with aluminium and titanium. Next slide, please. We can also look at it using Raman spectroscopy. We've shown two of the grains here. The top one refers to the CL image right at the top right there. The bottom one shows a better crystal with CL imaging with oscillatory zoning, and that's the Dalwitz-Nunatak one. If we take the bottom one first, what you can see in the Raman images, the intensity, the shift, etc., what you can see is the crystal is somewhat disturbed, but not very much. However, when you go to the gauge ridge sample, what you can see there, and I've labeled them here, you've got three domains essentially: a moderately radiation damaged zone 1, which is giving you the sort of greenish color. You've got a more damaged area, which is giving you the blue color. And then you've got this dark area, which is a glassy area. Again, if you remember, I mentioned if you alter these zircons, we call this metamict. These are metamict portions of the crystal. But when you look across that crystal, you can see that there are portions which still have some crystallographic structure. Next slide, please. So we're going to go through our model for how we think these things formed. Why do we have spheres, nanospheres of lead in zircon? And of course, you can probably work out for yourself. You can see the implication of this. If you have enough of these and you put an analytical spot on top of them, you're going to get a very funny age. And in fact, you're likely to get an age which is older than the age of the Earth. But let's go through this diagram. So what we've suggested is, no, sorry, go back one. Yeah, on this diagram, this is the normal state we'd expect in any zircon crystal which has been around for a long time. We've got lead developing in zones because we've got uranium and thorium decaying to the lead isotopes. So what we would have here is areas which are radiation damaged. So they're the ones which are colorless with the little red dots in. And the other one is the areas where the lattice is remaining in a reasonable state. Okay, next one, please. But when we heat this, what do? Well, if you heat it, you cause a bit more disarray, if you like, in terms of the lattice arrangement, but you also start to form melt inclusions. Next click, please. There we are. What we do is increase the lead nanosphere size by Ostwald ripening. In other words, they grow bigger and bigger, and they start to congregate, and they start to fuse together. Next slide, please. Then, as the thing starts to cool, the lattice starts to recrystallize and become more coherent, and it isolates these things into these little lead spheres together with the silicate melt. In other words, they're like melt inclusions. Next slide, please. And there at the bottom, we find that the lead clusters are formed by this process as it cools after the high temperature metamorphism. They're associated with those elements. So that was our model for the Antarctic zircons. Other people have since found these phenomena in zircons. They've come up with slightly different models, but there is no common model to explain exactly why we get nanospheres, but we do know that they're fairly widespread in rocks as young as 30 million years, in crystals as young as 30 million years, from rocks at that age, back into the Hadean. Next slide, please. So, just to give you a summary of what that means, we have lead present as metal nanospheres, 10 to 30 nanometers in size, randomly distributed, but always within these recrystallized or metamict areas. The nanospheres are commonly associated with the quench phase silica and titanium aluminium. There's the glass, and we believe it was the UHT metamorphism. If you heat the rocks to 1,000 degrees plus, this is very likely to happen. Next slide, please. Okay, case study 2, back to Jack Hills in Australia. This was Aaron Kavos's oldest zircon, which we analyzed in Perth, 4383 million-year-old zircon, but it had a rim at 3380. And so this was selected for, again, the first study of its type on zircon. This is the atom probe, the Kamika atom probe, which just happened to be built in Madison, where John Valley had his Kamika. So You can probably just see the rim there. I won't go into the details. Next slide, please. Here are the old crystals, or the two ages, let me say, on a Weatherall plot. So you see we've got a group of ages very close to 4.4 billion years, and then we've got some event at 3.4 and the the normal discordance of that data. So we've got two ages in the one crystal. Next slide, please. Okay, how do we do this? This is a FIB machine, focused ion beam. It cuts a slice, which is widely used in TEM work. You need to take a very, very thin slice through your crystal. Actually, the shape of this crystal, the shape of the FIB is different for atom probe. It's actually a wedge shape. If you look at the diagram on the bottom right, that gives you the shape of which this FIB is cut. It's not parallel, it's cut as a wedge. Why? Because we want to cut that FIB into a number of needles which are of that shape so that we can analyze them. Next slide, please. This is the Kamika Leap 4000X, which is the machine that we're using. This is I think there's maybe one other update of this. We purchased one of these 3 years ago. This machine was mainly used for looking at metals. You can see on the right an example with tungsten, iron, nickel, and Cu in there, copper. It was used in material science. This was the first instrument actually at Curtin University in Perth, which was bought for geoscience. Next slide, please. This was done in Madison. This is the Valley et al. Paper. What you can see here is a slice through the needles. So the left-hand needle, portion of the needle, is lead. It shows, you can't really see it too well on the image that I'm looking at, but it does have concentrations of lead. Interestingly, in this crystal, there was concentrations of yttrium. We didn't find titanium, aluminium, or silica, but we found yttrium. And then you can look at these clusters in the large image in the middle there, the big one, which shows there are clusters. And when you look at those clusters, what you can see is it's a mixture of yttrium and lead. Now, there's no inclusions. They're not mineral inclusions. They're just atoms. There's no nanospheres in this example from Jack Hills. And recent work, which is yet to be published, shows that there are nanospheres in there. Okay, a typical lead cluster has a very maximum concentration, only 0.2% lead. It contains about 4,000 atoms. In 20 nanospheres, if we had that, assuming lead, we would have 139,000 atoms of lead. So there's a difference between a nanosphere and a cluster like this. How do we explain those clusters? Well, we explain them as simply alpha recoil produces the lead from the breakdown of the uranium, but what happened at 3.3 was it was metamorphosed, or 3.4, it was metamorphosed, and this metamorphism provided the heat, which again concentrated the lead. It didn't produce nanospheres because the temperature was probably not high enough, but it did produce concentrations. Next slide, please. Let's also look at Jack Hills and another study with my postdoc, Rongfeng Ge, who's now back in Nanjing. We looked at a series of very good, very precise, dated crystals of zircon from Jack Hills. Next slide, please. And what we found, we thought we had the oldest crystal on Earth. You remember, the oldest crystal on Earth is 4404. Here we had an age of 4486 plus or minus 17, and a series of other ages over 4.4 billion years, over 4.44 billion years. However, because we'd already been working on this problem, we realized we better check and see if there's a problem. So we took this to Stockholm and we ran it using ion imaging. And on the diagram on the right, you can see the Concordia diagram of the data as it came off the shrimp. So this would have been 60 million years older at least than the oldest crystal on Earth, if it was true. Next slide, please. Right, these are the ion imaging, or images of that particular crystal. On the left, I think we got 206 lead, top left, top right, 207 lead. But again, that light spot indicates a concentration of both those elements. both those isotopes of lead. We do the same thing. As you can see on the bottom diagram, we can use that wind imaging technique to look at domains, to look at theoretical analytical sites, and look at the ages. I want to point out, if I can see it, right down at the bottom left diagram, 1, 2, 3 from the bottom, we have an age of over 5 billion years. Now, clearly this is wrong. It's older than the solar system. So you can't have your zircons on Earth being older than the solar system unless something very odd is happening. In fact, you can't have them in the solar system unless something very odd is happening. So we know then that this lead has also been mobile. But interestingly, we haven't found nanospheres in here. We've just found these concentrations. If you look at the top right diagram, which is the lead 207, you can see that some of the concentrations seem to be following a structure in there. And that, in fact, is a structure in the CL. But this little spot is the interesting one, because when Rongfong was doing the analysis, he happened to put a shrimp spot on that site, and it's 20 microns. And so he got perfect data. The data said, this is a concordant zircon, bang, this is the age of your crystal. It isn't. Next slide, please. So here are the data. Top left diagram is showing, I'll just point out the blue one. That shows the variation when you analyze different cycles through your crystal in the single analysis. This is the variation in the 207 lead. So we're seeing this lumpy lead effect. I won't go into the other ones, but you can actually use the wind image calculated data and plot them on Concordia. And there's your 5.2 billion year age crystal, which is reversely discordant. So we can calculate a few things on that if we want to, and that's all in this geology paper. Next slide, please. Here's another example showing the variation in the elements as we analyze them. These are a whole range of zircons. The important one is the one on the bottom right corner, which shows this lumpy lead effect. Next slide, please. Right, what do we conclude from that particular study? Well, the data from the SIMS seem perfect. They're concordant, they're reproducible. However, when an ion image was taken, it shows that the lead, PB star means radiogenic lead, has been redistributed. So this allows calculation of ages up to 700 million years older than the true age of the grain. This becomes more and more important in geoscience because everybody tries to get their spot size smaller so they can analyze smaller portions of zircons and other minerals. This is the danger of decreasing the spot size. You introduce things that you don't really understand unless you do all the background work in detail. The true age of the grain is actually 4277, and the lead was mobilized at 3.8, which is the age obtained from the rim of that zircon. So again, it's the same phenomenon that we saw in the study by Valley et al. Therefore, even concordant and Concordia ages, which we could calculate, they're the best sort of ages, can be wrong. So to solve this problem, we argue that really, when you're looking on old crystals, the Hadean ones in particular, you really need to do this ion imaging technique using at least a Kamika 1280 or Kamika 1300. Next slide, please. Right, the very last thing I want to talk about is some of the issues with the lutetium-hafnium data. And this is a paper we did with Bill Griffin from Macquarie University using Elena Belasova's database of 6,699 zircons. You can see the age across the top. You can see the age across the bottom, if you like. So 4.5 at the top there, 2 billion years as far as we went back in the data. The histogram at the top shows the distribution, if you like, of zircon age data in the database. What it shows really is that there's very few in the Hadean, which is shown as a blue area, and even in the Eoarchean, there's not too many. It increases, of course, with time. Yet the second diagram is our epsilon hafnium plot, again with the mafic source, this time plotted at 0.024. The felsic source, not strictly the felsic source, that's Bill Griffin's whole of crust source, 0.015. And then if you get a lutetium hafnium ratio of 0, it means something's gone wrong with your crystal, it's been totally reset. Okay, here's the spread of the data. On the right-hand side of that diagram, in the Hadean field, you can see the Naria terrain, you can see a castor material as well. So these are the Hadean crystals that have been recorded at the present time, most of which, as you can see, if you draw the line at 0, would fall below the Chur line. And the bottom diagram, again, shows the possible evolution of those data. So next slide, please. Let's go back to this data of Wang Chan and point out that most of the data are below zero. Some are greater than zero, but they're not really greater than +5. We've tested some of those, and we believe that one or two of them probably correct, because we've got an identical Sims age on the same site as we collected the hafnium age, because all the crystal wasn't totally destroyed. But that's, as I told you earlier on, it's difficult to do. You should do all the microanalysis first, leave the ICP-MS till later. Next slide, please. So we don't know where these crystals came from. They're detrital. So how do we work out what they might be? So we can apply a lutetium-hafnium ratio, and we can calculate the model age. So if we look at the top, we apply a lutetium-hafnium ratio, which is consistent with really felsic rocks, granites, 0.011. We find that most of the crystals actually fall in that field. I don't know whether you can read it, but at the bottom, we have 4.6. We have older than the solar system. So it doesn't take into consideration all the crystals. If we apply Bill Griffin's continental crustal value, 0.015, we see there's quite a few crystals will give us age, or sites would give us ages up to 4.8 billion years, again, older than the solar system. Even worse, if we apply the mafic ratio of 0.22, we find that we get up to 5 and 6 billion years for the model age. Clearly it's wrong. So next slide, please. Going back to those data, what we can see is a spread of data from various authors for at one site at Jack Hills using different samples, but from the same site. You can see in the pale blue the sites which have much elevated value. Next slide, please. Right, on the diagram on the left, we have Mark Harrison's first paper on Jack Hills. On the right, we have a paper I did with Tony Kemp. You see a big difference. Again, zircons from the same site, the W74 conglomerate. What do we see on the left-hand side? We see a lot of data plotting above the bulk Earth value, the zero Chur value, going up to +15. On the diagram on the right, we see no data above the Chur line. Right, why are they different? Harrison et al. Used multiple methods, solution plus in situ ICP-MS, and they used a very large spot size when they did the in situ ones. Remember, this is a preliminary study, so you can't be too critical, but it does indicate if you mix your techniques, you introduce a problem. The large spot size meant that you took a large sample volume, and because the zircons are complex, you probably got mixed ages. They also did not collect hafnium and uranium lead simultaneously. They collected the uranium lead first, and then they applied that to the hafnium data. It is likely then that a wrong age was assigned to that data, making it an incorrectly positive value. I can't read it, but I think if I remember correctly, if you have an age incorrect by 100 million years, you're somewhere between 2.2 and 2.5 hafnium units wrong. And so it's quite easy to get up to 10 hafnium units, which are totally incorrect for that sample. I should point out that in the study with Tony Kemp, what we did was we simultaneously collected uranium, lead, and lutetium hafnium data, not by split stream, because it wasn't invented then, but by peak switching. So we switched from one to the other. It's not quite synchronous, but it's more or less. Next slide, please. Also part of the Kemp study, we looked at rocks that Bob Pigeon and I had analyzed many years before from the surrounding belt at Jack Hills. If you can go back in your mind to that very early diagram I showed you, there's the Jack Hills belt. Either side, there are young granites and old TTG granites. So we analyzed both these. Notice all the data for them fall below the Chur line as well. And then you can plot a mafic crustal line which goes back, and you can say, wow, it looks as though we're reworking Archean material. So there's no evidence of depleted mantle being involved, no new melt coming in. It's just a reworking of Hadean crust. So this is a totally different interpretation from the original Harrison data, which suggested that there was mantle overturn and therefore plate tectonics at 4.4 billion years on Earth. I must be honest, though, when Harrison and Reed did this study, they also, when they used a better technique, they also found that there was no positive hafnium. But the other one is in the literature. Okay, and there's my comment about the 2.2 and the 2.5 epsilon units. And we know from Kavosi's work that many of the grains have 3.6 rims. So here you're getting the built-in error if you don't analyze in the same spot and you don't analyze simultaneously. Next slide, please. I think we're getting to the end. I think these really are my final comments. So my comments would be very careful with your analysis, prepare them, your samples the best that you can, do as many techniques as you can to image them prior to analysis, select your sites very carefully. But note, even if you do this, you can get the wrong answer. So we're learning all the time. Perhaps ion imaging will become much more widespread, but certainly with old crystals, we need to do this where we have multiple ages in single crystals. Next slide, please. I think that would be it. It is. This is Jack Hills. Gracias. I know we're rather late as we're going on here. It's getting very late in Colombia. It's almost lunchtime in Perth here. But if you want to ask any questions, I'm happy to try and answer.
Thank you very much, Professor Simon. Si alguien tiene una pregunta, bien puedan aprovechen al Profesor Simon que lo tienen aquí. Les dejo el micrófono abierto.
Wait on, I must go and get my translator, Anna Ibis. Let's see if she's around. Just a moment.
Thank you very much, Simon. Have a good night, a good day there in Australia.
Okay, I'm back with my translator.
Okay.
Please, can you please ask the question again? No?
I do have a question, but I'll talk to you in English if you don't mind.
Yeah, that's even better. Thank you.
Okay. I'm more interested on the use of zircons in terms of recent provenance studies.
Right.
So on the reverse discordance plotting diagrams that you showed of lead versus uranium in the Antarctic zircons, the Concordia, the Terra Westerberg, I don't know what the Concordia diagram.
Yep.
You showed that there's a lead increase in zircon crystals.
Mm-hmm.
In terms of chemical and physical durability of zircons, could you potentially use the analysis of presence of lead or other different elements in zircons, including radiation damage in the crystal due to alpha decay, as a proxy for laterization or basically degree of weathering?
You can do. A colleague of mine, Bob Pidgeon, Pidgeon, has published several papers, including work on the Jack Hills, where he's looked at the water content of the OH content of zircons. And this is the conclusion that he believes that this normal discordance of most of those Jack Hills crystals is the result of, I guess, fairly recent weathering, although it's fairly prolonged in Western Australia. It's probably 30 million years of lateritization on and off affected the whole of the Yilgarn craton where we're working. And he believes that not only has the water content been an important factor, but that uranium has actually been introduced in some of the crystals, which would make actually an interesting reinterpretation of the lead loss curve, because it could also be a uranium gain line in Discordia. And we know that the uranium fluids have been quite active in the Yilgarn craton. There are uranium deposits, not in this particular area, but it's quite common in the groundwater. So yes, you could use that, but if you check, I can't remember exactly where they would be, but what publications. But if you could send me an email, I can actually send you Pigeon's publications, or you can put him into ResearchGate or something and find him, I think.
Will do. Thank you.
Thank you.
Simon, I have a question to you.
Yep.
In all your projects and research, have you found these lead spheres to be common, or aren't they?
Yes, we found them to be present, particularly in, well, both UHT and UHP rocks, and we found them, well, a lot of these things are not published, so I have to be careful what I say, but we found them on several continents. We found them in Europe, in the Baltic Shield. We found them in the Castor terrain. We found them at Jack Hills in a more recent work. And we found them in several other locations. So they're actually more common than you'd think. And we found them in crystals which are not always obviously undergone a later metamorphism, which is causing a bit of a problem at the moment, because that story seemed to work fairly well for UHP and UHT rocks, but it's not working so well for crystals which we can't prove ever went to medium or high-grade metamorphism. So there are some issues which need to be resolved, but yeah, they are occurring quite widely. And it's one of those things, once someone finds the first one, you know, other people work on them, and they start to find them in unlikely places sometimes, but also in the expected places, which are other UHT and UHP terrains.
Perfect, thanks. And are they mainly in all terrains, like cratons, or can they be present in younger terrains? It just matters.
Yeah, they're present. They're present in younger terrains. They're present in terrains as young as 30 million years, which means that you don't require time to actually produce these. You need some sort of condition to produce them, obviously, but it isn't as though they only occur in ancient crystals, which is what we thought initially. So we found them in younger rocks. These will eventually get published. There's a massive data that we've collected with Monica Kusiak, Martin Whitehouse, and Richard Wirt in Potsdam. So we have a lot of data which we need to get out, and probably this coronavirus is going to help us to get a lot of papers out.
That's good. Thanks.
That's really good time.
Thank you, Simon. We have another question from Christian Romero.
Yes.
He asked, what good modern lead contamination look like for the treated zircon sample in a Weatherhill or TW plot?
Sorry, I didn't catch all that. We were sort of breaking up a little bit there.
Okay.
Can you repeat? Yeah.
What would modern lead contamination look like for a treated zircon sample in a Weatherhill or TW plot?
What sort of contamination was it?
Lead.
Lead contamination.
Yes.
What would it look like in a what plot?
In a TW plot.
You mean titanium?
You may see the questions in the chat.
Okay, let's have a look. Sorry. The line still isn't all that great here. But
At the end, there are some questions.
if you want to do it in Spanish, Anna's here. If you can do that.
¿Cuál es la pregunta? Ana, ahí el Messenger están todas las preguntas en la parte final. Tiene como 4 o 5 sin responder.
¿En qué parte está de la pantalla?
Al lado de las personitas hay una notica. Dale enter ahí y te aparecen todas las preguntas.
Listo, ya lo vi. You have all the questions in this here, so you can
Okay.
one by one and scroll down.
So I can see some questions and some thank yous. Thank you. Let's have a look. Oh. Doing.
Chat.
Yeah. Okay. The question: what do you know about the use of dating method for samples of? Oh.
This is the question.
Oh. Okay. What would modern lead contamination? Tridal zircon in a weather or Terra-Waterberg plot. Yeah, okay, I've got the question now. If you can still hear me. If you added lead to the system and you had let's say a Terra-Waterberg plot, and what it should do, depending where your data would sit, if you analyzed away from the lead, it would obviously shift it towards the lead gain portion of the diagram. The problem is, I don't know how you would get modern lead contamination in a zircon, except perhaps along the cracks. And the issue, of course, is if you have cracked zircon and a zircon with inclusions, you tend to avoid those during the analysis. So you probably wouldn't, unless you were specifically wanting to hunt that type of zircon, you wouldn't normally analyze it. But clearly, if you've got modern lead contamination, where you saw that the aluminium and the iron were actually moving into the crystal, then if you put your analytical spot on there, again, it would depend on the isotopic composition of the modern lead, assuming it might have a high 204. The problem then, of course, with the analysis, if you have a high 204, you have a large correction of your data. And I didn't go into this, but of course, this is an issue with hafnium analyses as well, because to get a good hafnium analysis, you really want to have a reasonably concordant crystal, because if you can vary, if you move along the line, along Concordia, you can actually produce spurious ages, which are a lot older than the age you actually, the actual age is younger than the age you would record with the hafnium, because it's sitting very close to Concordia. People are now trying with lutetium hafnium analyses to actually do a common lead correction. Some labs have got quite an intricate process to do that. If you don't have that correction, you can have quite a few spurious results. And so you have to be careful on that point as well. So again, it would depend on the composition of the modern lead, I guess. And that's probably about all I can answer on that one. I see the next question was, what do you know about the use of dating method for samples of limestone with carbonates and prehistoric caves as well? I don't know much about that, but my colleague John Valley at Madison does quite a lot of analyses. In fact, they probably do more analyses of this than they do with uranium. Well, he never did uranium lead, he only wanted oxygen, but you can date it. There's also a guy at the University of Queensland. Personally, I don't know much about the technique. Many years ago, we tried to date rocks from the Aldan Shield in Russia with the late Borming-Jan. He collected, and he did lead isotopes on the carbonates in the Aldan Shield. I think he might have published that, but to be honest, I don't know the results. But yes, there are people working on these limestones, trying to get reasonable ages out of them. Next question was, what other distinguished features help in distinguish igneous to metamorphic titanite and monazite? That's another interesting question. Again, it's very different from zircon, which I was focusing on today. Titanite, although the closure temperature of titanite is believed to be very similar to that of zircon, our experience is that titanite tends to be slightly younger by perhaps 20 million years. We've done a fair bit of work in China on these problems. We've also looked at India as well in the Darwar craton. Monazite, again, it's a bit difficult with monazite. It depends how you date it. We use SIMS here, but people still use the CHIME method, the chemical method of dating, which is quite good because it does show you variations across crystals. In fact, I should point out that lead nanospheres have been, or put it another way, I'm not sure they're nanospheres, but there's certainly concentrations of lead have been found in monazite. So it looks as though monazite is affected by the same processes that zircon is as well. There are some papers on that. Sorry, I can't, off the top of my head, recall the literature, but if you did check that, certainly for monazite, titanite, I've not heard of any problems or with nanospheres or with concentrations of lead, but they may occur. We know, for instance, with bedelliite, that there's a crystallographic effect. So if you date bedelliite with a crystal oriented in one direction, and then you look at one that's 90 degrees to that, you will get a different age. That was Mike Wingate many years ago working with Bill Compton in Canberra. So there are issues with all these minerals that we use. The reason I focused on zircon here was because it's so ubiquitously used that it's very important to realize what some of the pitfalls might be if you start analyzing and don't really interrogate the data properly. I'm just going through these questions now. What would, and we had modern lead contamination. Here we have another one. What are the distinctive features that help you distinguish? Unfortunately, it seems to disappeared. I don't seem to have got any more questions I can see in my chat, but if you've got any, oh, here we go. I'm going backwards now. In the absence of big zircons, how accurate is the monazite dating? Well, again, there's no real problem with monazite dating. Sometimes there's an issue with the thorium content and so on of monazite. We've tried to date the famous Bayan Obo rare earth deposit in the north of China, and it's got very little thorium in it, which is very unusual. And so we haven't been able to do that. But yes, monazite dating is pretty good. What's the distinguished features? Oh, I think I've answered that. Okay. I can't see any more direct questions. Is there any more there?
Professor, thank you very much.
Yes, it's my pleasure. I hope you enjoyed it. And I hope you followed it okay. And take care of yourselves in Colombia, like we're doing
Thank you
here.
very much, Simon. It was a pleasure to hear to you.
Thank you. Right. Goodbye.
Bye-bye.
Have a nice day.
Bye.
Goodbye. Gracias, Clemencia. Buenas noches a todos.
Bye, thank you. Ciao.
Bueno, gracias, Clemencia. Creo que había intentado grabar, como me decían que nadie estaba grabando. Voy a ver si lo logré o no.